deal with this slow animation. Hopefully things work.
All right. Hello, hackers. It's access control and cryptography time, which is actually kind of interesting. The camera's not following. Let's get it following. Gesture-based cameras. Awesome. Okay. Um, it's an interesting combination because then you have uh, clear connections between these two topics, and it may be a more strong way than in a similarly strong way as intercepting communications and cryptography and so on. So hopefully everyone has had time to review the access control lectures by guest professor Adam Dupay. He's our access control guy. He controls access to a lot of things, including some part of your grades now. And hopefully the material has been pretty approachable, right? Maybe even compared to previous things. Speaking of this, so let's take a quick check-in on how crypto is going. It is going in this sort of inverse exponential over here fashion. Crypto is definitely much harder than anticipated. We've are always tweaking the modules, of course. In crypto, we added a couple of extra challenges this time, and the difficulty is definitely there. So 18 people solved the whole thing so far. That's great. Everyone else keep pushing. The deadline is tomorrow night. So now is that final push. I guess if you've been procrastinating, the procrastination's over anyways. But I think it'll be difficult to go from here to solving crypto in a day and a half. Do you think you could do it?
I mean, if I spend my entire time doing it.
So Connor thinks that if he spends his entire time doing it, he could do it. All right. Awesome. So far we have most people with a 58% of challenges solved. Now, if you solved the checkpoint, which mostly is in this module, data encoding, decoding, etc., and then some light crypto. If you solve the checkpoint, which 91% of is that checkpoint on time or just checkpoint? Just checkpoint. Okay. Well, if you solve the crypto checkpoint, that's already 3% to your crypto grade. And then the median 38% completion of crypto, if the module was due this minute, and we're not gonna make it do this minute, that would be a funny joke, but I won't even make the joke. If it was due this minute with 3% of your grade, or 3 out of the 10 points basically of your module grade determined by the checkpoint, and 38% of the other 7, you have over half of the of the points you're going to get from this module. But anyways, keep pushing and keep doing crypto. Access control, on the other hand, very few people have started it. The people who have started it have sped through it very, very quickly. You can get 80 to 90% of access control done very straightforwardly, especially with the Linux Luminarium under your belt and with the lectures. Later on, there is a challenge or a series of challenges that relies on automatic interaction with the challenges, which we'll cover today. But access control should be a kind of bit of a straightforward for you guys. All right, let's look at helpfulness. Now, why did this happen? Because we changed the way this was being calculated?
No, this is using the old way.
The old way, like just the total number of upvotes. Yeah. All right, so The tables are turning, so I am somehow managing to gain on Robwaz. This is maybe a example of work smarter, not harder. Robwaz is on the Discord every hour of every day. Only Hanto is more present on the Discord, and Kanak in fourth place on helpfulness, and I turn in fifth place. So great job, I turn and obviously Hanto, and everyone else keep zooming up there. Canlex is number 24th here. Who else do we recognize? Some of our brilliant TAs. Awesome. Okay. Anyways, let's roll on. How are people currently doing in the class? So if you haven't had one of these, we'll start having them more now that we have some amount of modules under our belt. This is if the crypto module is due today, right?
No, this is
ignoring crypto. Yeah.
Ignoring access control.
So ignoring crypto and access control. Most people in the class are doing pretty well. We have a fail rate currently of about 15, maybe 17%. A common fail rate at 300 level is what, like 30? Yeah. So, things are seem to be progressing. I realize crypto is going to probably change this distribution significantly. But, we'll redo this graph again on Monday and see where we're at. This also doesn't include extra credit, but we're about to launch a feature where we'll actually automatically pull in your meme and thanks extra credit. So there's less ambiguity around that. And maybe we could expand it actually to pull in the CTF extra credit as well. And then that'll cover the majority of extra credits. Okay, cool. Sounds great. Any questions on this? Awesome. All right. While we are here, let's grab a scoreboard of the whole class, and we'll see. Let's see who the crypto super people are here. All right, we got Shadow Immune. Shadow Immune sounds familiar. They were on top of another scoreboard recently. Wingdeans, Black Dog, C Steedman. Great job. Oh, and Navigna Ready. Great job on the top 5. And then if we scroll down, there's still 3 slots left in the top 20. So you can have your you can solidify your glory. What's interesting here is the lowest number of solved challenges. 56 here, but we only have 18 people that have solved 100%.
It depends on when they solve it.
Yeah. So it's okay, cool. And overall scoreboard, if we go for how people are doing in the class all time. There's Shadow Immune is better at crypto than the average thing, but we got our top 5. Eli, allegedly Richard, Shadow Immune, Caden, and good job. And this is interesting in that only the top 3 is determined here. Yeah, on all time. So you can still get up there in the top 5. Okay. What did I want to say about all this? Oh yeah, if you don't want to show up on these scoreboards, you can go to settings and change yourself to hidden visibility, and then you won't show up on scoreboards and won't impact anything else. Okay. That's it. That's all the administrative stuff. All right. Just remember, crypto is due tomorrow night. Access control is due Sunday night. Checkpoint of access control is the same time as the due date of access control. And yeah, that's it. Okay. Let's talk about some access control concepts that are interesting, that apply to modern world systems that we don't yet cover in lectures or challenges necessarily. And then we'll also talk about the most complicated part of access control, which is interacting with the challenge programs automatically. Okay, I'm just gonna use the stream from the beginning, if that's okay. All right, so say we're on a box here. We all know that if you create a file, it has some permissions, right? This says it's user read writable, group read writable, and world readable. We can cat it out. If we say, hey, we want to remove all permissions from this file, we cat it out. You get permission denied. All right, everyone's on board here, right? Should be 100% review so far. Perfect. All right, now let's make this root owned, root and group root owned. Here's the file now. Still permission denied, of course. If we say, okay, the file is readable again, so this is a different type of way of specifying the permissions that you have learned in the lectures. The second or third lecture for this module, Linux Luminarium, taught you this style of specifying them symbolically with these letters and numeric permissions Adam discussed in the lectures and you practiced in the homework. All right. So here we are. The file is readable again. All right. Awesome. Compared to showing off crazy crypto stuff or web vulns, this is not rocket science yet. Okay. Now, a cool thing here is that if we, let's see, what order do we want to do this in? Let's make another, let's bring this back to us. So this is now our file, okay? Cat it, that's great. Again, we chmod it to be no permissions. Can't read it out. But if we become root, oops, we still have no permissions. It's not even owned by us. It's someone else's file with 0 permissions, but we can cat it. This is an interesting property of Linux. Is it a POSIX property? Anyways, it's an interesting property of Linux where root can basically override permissions checks for certain things. And these things include reading files. They include writing files, even if the file has no read or write permissions. And they include entering and listing directories. They don't include executing files. I'm assuming as a safety precaution, because if you could accidentally start executing random files as root, that's not great. But reading and writing, I'm actually a little bit surprised from a security design perspective that root is allowed to override the write permissions. That seems like a safety issue as well, right? Because if you trick a process that runs as root into writing random files, that we had an infrastructure level vulnerability just recently where people could escalate privileges on every challenge in pwn.college as long as they could trick a challenge into writing to a directory. Okay, so TLDR root gets to override file permissions. Super interesting. How does this work? Well, it used to be in the old days that in the Linux kernel somewhere, and the Linux kernel is open source, you can look up the source code of the Linux kernel. Used to be that there was just a check somewhere. If the user ID was 0, just return that, yeah, you have access to this resource. That's not the case anymore. I'm pulling this number out of my hat just based on vague recollections, but somewhere like in the late 2000s, Linux moved to this capability model. Even before that, actually, probably the mid 2000s. Anyways, where every process has a set of capabilities that allow it to do various things. Set up network. You might have seen in the network module. Do we have anywhere where we mentioned cap net? Yeah. So all these cap underscore in all caps. These are capabilities. These are properties of a process that grant it special access to certain resources. And you can get the capabilities of your process using get caps. And if you recall from Linux Luminarium, every process has a process ID. Our shell's process ID is stored in this special $ variable. So if we get caps $, we can see that we have no capabilities. Why? We should have stack override capabilities. So as usual, we are demoing something that's so basic that we don't need to practice, and it turns out that we needed to practice. All right. Okay. Current, nothing. We are root. So these are all of the possible capabilities that we could have. This is the capability that we're interested in. Capability of data access control override. Why is it not showing up? It is the one sec. When we are confused here, of course, we can go to, oh my God. Yeah, now I'm getting the lag. And we're using Mac OS to stream. It's not as turnkey and reliable as Linux, but it happens sometimes. Okay, let's do this. Here we are now. Cap sh. Okay. Let's so E is the equal E. Yep. Is it? But we should have all of these capabilities right now, right?
What is cat access status?
Let's go straight to the source. Okay. Yeah. We should have all these capabilities, right?
Yeah.
Okay. Yeah, we don't have these capabilities in our user shell. Yeah. There's irrelevant stuff that becomes relevant. Okay. So we printed out current equals EP. What do we do when we have a brain dump? We go to Google and we type in, and I'm going to claim we meant to do all of this confusion stuff so that you can see how to figure this out, but don't listen, don't believe that. What is EP in kappa H? All right. If the process set shows equals EP, that means that's all the capabilities from the bounding set. Awesome. Okay. Let's go a little deeper into Stack Overflow. This is looking ahead. E is effective. What is P? P is permitted. Permitted. Okay. Awesome. Capabilities will put in the permitted set, and all permitted capabilities will be copied to the effective set. So this is in the are we still streaming? I might have fucked something up. Nope, we're still streaming. Okay. Okay. In the lectures, Adam discussed something called role-based access control. Right? You remember the lattice with the whole thing. This similar that same theory is being used here in Linux capabilities, right? In where we have a set of all potential capabilities, a set of capabilities that a process is allowed to take on, and then a set of capabilities that the process does take on. And in this case, going back to the source, each capability is a bit in this field. Is that actually, that's a lot of capabilities? That's not. Okay. Yeah. And then the capabilities that we are permitted to have is that our process is permitted to have are bits in this field, and the capabilities that we have are bits in this field. Okay. This is a bit of a cluster situation looking at an interactive shell of a user. But the interesting thing about Linux capabilities is that they actually live not just on users, but they can be granted to processes spun off, launched using specific files. So for example, going back to my user, I don't have the ability to read this file, but if I copy in bin cat, right? Cat is just the program that cat's files that I've been using this whole time. It doesn't have the permissions. Of course, the file has no permissions. But what we can actually do in Linux, which is pretty cool, is something you're used to. Let's start with that. We can tell cat that, hey, you're running. You're going to run as, when I launch you, as whatever user owns the process. This doesn't help us because stream owns the process. But then if we make cat owned by root and reapply that set UID bit, which is removed as a precaution when ownership changes. Now, when cat runs, it'll run as root. And now we can override the data access controls again. Okay. But running things as root is dangerous. It's the violation of the security boundary that you implicitly do every time you interact with a challenge. The reason that our challenges can read the flag, whereas your normal user shell cannot, is the flags are only readable by root, and the challenges are set UID root. So when you run them, they run as root, just like cat in this case. So you don't always want to set UID everything that needs some special access to the system. So let's back up. We've reset cat back to being owned by us. Cat, once again, cannot read my file. But what's really cool is we can actually set the data access control override capability onto cat itself. And now we're going to fumble a little bit with this and learn how to make this work. So we have a couple of, there's the setcap utility that will do this for us. We can we have to specify the file name. Okay, that's great. Then we can specify a bunch of capabilities. So cap DAC override. And of course, this has to be done as root because it itself needs some capabilities to do. Let's see if this works. Invalid argument, we need to maybe it's the other way. Oh yeah, it's the capability and then the file. Invalid argument. Set cap. Capability is specified in the form described in cap from text. Maybe we I mean, my guess is cap underscore is gonna be take. Okay, never mind. Move read capability text cap. What does cap sh that suggest do here? Dash suggest. Search cap descriptions for text. Okay. Okay, now here it is. Cap DAC override. See, it has this capability. Cap DAC override is this bit in the capability bit mask. Very cool stuff. Can we just use cap sh? This is okay. What is? I mean, this is fine. We can. All right. Dash r dash or the caps list file name. All right, let's just check it out. Set cap usage example. Plus, okay. Plus, okay, here we go. So that's, oh my God, I clicked something. This macOS stuff is a meme. All right. What do we want to do with cap DAC override? Here we're just specifying it. What we actually want to do is, hey, and actually we don't want my file, we want cat. We want to say, add this capability into the effective list, the inherited list. These are capabilities that can be passed on to children. We don't actually care about that for cat. And the permitted list, right? For cat. So if we do that, success. And now cat is just a normal file. We run cat on the flag. And even though the flag, or even though our file that we're reading has no read permissions, we as a user can override these permissions. So we have granted to the cat program some additional permissions that our user doesn't have, that the original copy of the cat program, for example, doesn't have. But this one does. And this is cool. So we've granted that to the effective and the permitted set, right? We can also instead just grant it to the permitted set. And actually, first we need to probably zero out all the capabilities. And then, so now we do, yeah. So it only has it now in the permitted set. And now if you try to run it, we have a permission denied because cat doesn't have it as an effective capability, only as a permitted capability. And from there, cat itself can grant itself the effective capability when it wants to use it as a sort of security measure, right? So it can adopt the role or not adopt the role. Likewise, we can grant an inheritable property of DAC override. And in this case, cat can give its children, its child processes, the capabilities of DAC override, right? Which is also useful in certain contexts. Now, this is like you might say, okay, but why do we really care about this? Well, you can use this to build very cool systems. You can use this to create a program that can run as a user, but interact with funky stuff with networks or funky stuff with other Linux craziness such as namespaces and so on. These capabilities are kind of an interesting role-based access control measure in the Linux kernel that people really know very little about. They know that, hey, when I'm root, I can read any file, but they don't know how. And this is how. Now,
files on the system that have capabilities granted to them.
Are there any files?
Actually use this. 1.2.24.04 use this.
It's an interesting question. So let's script this. Let's just do get cap, everything in user bin. Okay, ping. Ping, you can be a user, but still ping google.com. Okay, and that makes sense, right? Of course, we should be able to ping. You might have pung in the what's it called, in the intercepting communication module. That's great. But it used to be back in the day that ping was a set UID binary, and now it's not. Now it just needs the capabilities to be able to talk over the network in a way that's not TCP or UDP, which is, let me think about if this is accurate, more or less the only way that you can talk over the network as a user process, typically, a non-root process. Now, to talk ICMP, which is the protocol used by ping, you need to be, you need to have the CapNet raw capability. And in fact, if there was a security vulnerability in ping, as a result of this CapNet raw, is this true? Would you be able to sniff traffic, or do you need netadmin? Netadmin. Okay, but you'd be able to craft arbitrary network packets. You'd be able to ARP spoof all of this fun stuff if you could take over ping as a through some bug.
But you couldn't read arbitrary files.
But you couldn't read arbitrary files because, unlike back in my days, when I was hacking ping, I wasn't hacking ping, but back in my days, you could use ping to if you took ping over somehow, you could use it to read arbitrary files, etc. Okay. Couple of things I wanted to cover. Other interesting Linux shenanigans. You recall the concept of a file descriptor from a number of modules now, but including the Linux Luminarium originally, where you were you were passing Linux file descriptor between processes, redirecting, file descriptor 1, standard out, 2, standard error. et cetera, et cetera. An interesting thing with Linux is that it applies permission checks generally once when you first access the resource. Once you have, for example, opened the resource for reading, the resource is always opened for reading. So let me show you something interesting here. We're going to make this, how do I, okay, let's do, oh no, I made a terrible mistake. We need, I need a second, I'm just going to CMX this. I don't, do we have screen? Yes. Do I remember how to do, yeah, vertical splits? Okay. Okay. So now we have two terminals here. In one terminal, I'm going to look at my file and run up an IPython version here. All right. Here we are in IPython. Here we are.
Just a reminder the camera's in the top right.
Camera's in top right. Thank you. So here we are with the file. I can cat the file right now. And if I can, of course, open the file in Python, if I can type, and all is good, right? Can read it. Awesome. All right. Once I open the file, it's too late for me to protect this file. If I chmod 000, can we shrink this a little bit so that we fit on? There we go. If I chmod 000 my file here, I can't cat it anymore. Oops. Shit. Oh my god. I think oh, it's back. Okay. See, this is why screen is good. It comes back after a disaster like that. We're just gonna reset the terminal. Don't cat random binaries to your terminal. Okay. I can't cat it out anymore. But since I've already opened it, despite the fact that it is no longer readable, I can read it just fine. Access control checks are performed when opening a resource. Once a file descriptor is open, it's too late. The kind of foxes in the hen house or whatever scenario applies. All right. This is something very interesting because it also applies to directories, right? So the read the executable permission of a directory controls what users can enter into it. The read permission of directory controls what users can list it. And so if I enter this directory and then I create a subdir, okay, I can, you know, and then I move my file into here. This is all very cool. All right. If I chmod 000 this directory and I try to do cat out the file, I can't enter that directory anymore. All right. But if I, fuck. If I cd into this directory and into the subdirectory of it, and then, shit. Okay, I'm in the directory and subdirectory. And then if I chmod 000 dir, I'm still here and I can still operate, despite the fact that I can no longer get into this directory from another process. I am perfectly happily messing around, writing files, catting flags, and so on in a subdirectory of that directory. Now, I can't do this I can't enter the directory anymore. That'll tell me permission denied, but I no longer need to because I'm already there. Very cool. Another interesting quirk of Linux's file permission structure that's separate conceptually is the fact that in order to mess with a directory, like to create files in a directory, to rename them in that directory, I need to write permissions to the directory. The interesting thing is that I don't need write permissions to the file. And so if I create a file, let's say in this subdirectory, I have two files here. I have one file here. All right, I can make this file completely unreadable, but I can still mess with it. I can still move it around because I have write access to the directory itself. And you can think of situations where this might be a security disaster, such as shared directories, right? Like the temp directory. The temp directory has files from Connor's account, has files from Sam's account, has files from the stream account. And if I could just go in there and rename one of Sam's accounts, this is my, or one of Sam's files that another process, one of Sam's processes is using, and then Sam's process goes to read that file and reads the file that I moved into its place, that could be very bad. So I can move my files. Let's try to see what happens when I move some of Sam's files. So I'm going to move Sam's tmux. Operation not permitted. How? Why? I can move my files. Why can't I move Sam's? And let me just prove to you that normally speaking, in this case here, I could move someone else's files. ASDF is now owned by root, but since I have write access to the directory, I can move it around just fine. I've actually used this to root systems that I was permitted to root in real world environments, in real corporate networks. These vulnerabilities are very, very real, but this doesn't work. And the reason it doesn't, moving Sam's file in /temp is /temp is special. /temp has this little T here. A T is a flag in a directory. That's the sticky bit. That means that even if you have write access to the directory, you can only mess with your own files, not other people's. And actually, DAC override doesn't even override this for some reason. But if I have this situation here where right now my user can override or move around, rename roots files, or I can delete this file if I wanted to. If I apply, I'm just going to try to do this symbolically. If I apply the sticky bit onto the directory, I did something wrong. To just the user. Okay. Now we're going to Google for, no shame in Googling for everything. Oh, the owner directory can override it?
I believe, but Google.
Yeah.
Let's see how to figure this out.
So first, let's say figure out how to set the sticky bit. chmod-t. That was an AI summary, so let's man chmod to confirm that. I mean, let's just try it, I guess. Doesn't seem to have set the sticky bit. One 777. Okay, user sticky bit, which allows only the user to have write access. Okay. So numerically, 477 or 4 in the that extra 3 bits is the set UID bit. 1 is the sticky bit. Okay, now is this? Oh, I can still override it. So let's actually see. Test Connor's hypothesis. So here's the directory. My subdir is owned by root, but is writable by everyone. So I can still do this. Awesome. And now I'm going to add the sticky bit to it. And I can't. Okay, so the user overrides it. Learn something new every day. I am sure that I've had that in my head before, and it has fallen out. Okay, what else? Let's spend the last 25 minutes talking about pwn.tools, unless there are any questions about Linux access control mechanisms. All right, there was a question about the padding Oracle attack stuff. We went through the padding Oracle attack last Wednesday, right? Did you watch that stream? Oh, you were here. Okay. We'll take that one offline. We'll do right now. We'll do the pwn.tools stuff. All right. Let's dive in. Who here has been using pwn.tools? All right. So hopefully we can clear up any craziness. pwn.tools is it in the repos for some reason? I remember. Yeah. No, Python 3 pwn.tools. It's fine.
It's $4.
Yeah, as long as you stick to apt, nothing can go wrong. Obviously, all of this is already installed in the dojo. Okay. pwn.tools. Actually, let's run this from Python. pwn.tools allowed you to interact with processes, right? You can use it in a number of ways. People sometimes do this. I hate this, so I do this. But you can do whatever Python, whatever you feel comfortable with Python. pwn.tools allows you to start processes, read from processes, write to processes. And I wanted to point out a couple of things here. So first, you can launch a process, right? And you can launch a process by saying, we're going to create that in a second, right? This is all review. You run this and it says, okay, what syntax there? Oh, let's just manually run this in Python. So here we go. Okay. Boom. The process doesn't exist. Okay, that's fine. We're going to create it. Okay. Here's the process. Hello. And now we can run our boom. All right. we launch the process, and what the number one issue, one of the top issues people have with pwntools is they launch the process, they do stuff with the process, and then the Python interpreter, the Python script is done, the interpreter terminates and kills the process, and they didn't get what they needed out of the process. A good example is, it does something, and then it, sleeps for 10 seconds, and then it does something else, and, we launch this guy, and you can see this was a lot faster than 10 seconds, all right? So now we can do stuff like wait on the process, wait for it to terminate. Very helpful. This will take about 10 seconds. We can do stuff like read everything that the process has to offer. And let's change the 10 to 1. And now it'll read, and it'll actually wait until the process is gone. Boom. Versus we can just say read one line. Cool. Versus we can say if the process is a little more complex, read this again, common thing. You read one line, you forget to do stuff with it, your process terminates, and you're kind of out of the game. You can go into interactive mode, where it'll drop you in. Boom. Now you're interacting with the process. What is your name? Jan. And then in a minute says hello, Jan, and exits. Cool. Okay. Now, what if over here we do read all? We're waiting for the process to give us all of its data, and we're waiting, and we're waiting, and we receive 21 bytes of some shit, and the process isn't terminating because it's waiting for input. We didn't script that, and this is all very frustrating. All right. pwntools gives us some nice capabilities to easily add debugging. If you just add debug in all caps to the command line invocation of your script, it actually will print out what it received. And we can see at a glance, oh, that's what's going wrong. It's waiting for input, right? So now we'll do this. Then we can say, you can send line Jan, and it's better to stick to bytes or strings. And then we can repeat that read all. Okay, and then we run this, again with debugging, boom, it all works. Okay? I oftentimes, unless there is an absolutely unmanageable amount of debug output, I mostly run my tools with debug just to get that output so that if something goes wrong, I don't have to deal with it. Or if you actually solve the challenge, but you forget to print the flag, right? Do we have a fake flag in here? No. All right. This happens to me so depressingly much. I once lost an exploit race against Fish, one of my colleagues here, because I literally didn't print out the flag. And in between running the exploit the first time and the second time, Fish solved the challenge because he was smart enough to monitor the network traffic, so he didn't have to print out the flag. All right, anyways. Here we're going to see, okay, if my name is Jan here, it'll give me the flag. And in this x.py, if I do this, if I just print the next line, I don't get the flag. Right? Even if I am careful and wait for the process to finish, or I might do this and forget to print it, and it's just all very, very frustrating. All right. If I do debug, I don't miss this stuff. Boom. As a matter of course, I have the flag here, and you know what? If something goes wrong, I can see it going wrong right away. Awesome. Okay. Another thing that often happens with pwntools is you leave this out by accident, right? If all I had was this, debug wouldn't help me at all because I don't even ever see it receiving anything here. So oftentimes what I do when I'm writing pwntools scripts is I add a flush, a clean. This will clean the pipe. It'll listen for anything that's still left over and discard it. Well, it returns it from the function, but otherwise, if you don't save it off, it discards it. If you do a clean, you can often catch, with debugging mode on, weird issues where there's data that you're not reading afterwards. Could, in certain situations, save you hours of banging your head against the wall. The other thing is obviously all these reads are returning data. If we start complicating things a bit, echo password is, we'll have a p variable here. That'll be random. What is the password? Okay. We'll read, by default, read creates an input variable. Nope. An inp variable. Nope. A reply variable. Yes. Okay. So we see if the reply is the password, it casts the flag. So we do 28812, boom, the flag's catted. Awesome. Okay. Now interacting with this automatically is more complicated. So we need to, we could, for example, read the line and then split it and then take the last argument. That's our password. Too many. All right, and then print it. Let's try this. Yep, that gets a password for us. That's cool. And then we send line that password. And then we read the rest and we're golden. Except for, oops, I forgot to print it out. That's annoying. Hey, here we go. Debug works. All right. So this works. And it works because there is a predictable amount of spaces and whatever. The pwntools way to do this, that handles more complex situations, is we first discard everything, all text, until the word is space. Okay. And then we can just read the rest of the line, strip out the new line, and that'll be our password. And this works great too. It reads this first. We can print it out so you can see it. So it read the password, or password is space, and then it read the last thing. Cool? All right, now.
I think the pwntools way to do it is read line after. So pwntools has lots of functions.
Yeah, pwntools has a lot of, yeah.
There's like read line after it. Crazy.
Let's try it. Okay, read line underscore after, just after.
Read line after.
Read line after
is
password is, and then we strip it just in case, and let's see what happens here. Send line after.
Oh, there's only send line after?
There's no read line after. Yeah, all right. So, but this is interesting. We can go back to our working solution without the memes here. Read until password is, and then we read the password, and then we can, if we want to wait to send at the right time, it will ask what is the password. So if we say wait until it asks us for the password and then tells the password, and boom. In this case, it doesn't really matter. The program is simple. In complex cases, it can matter. Now, failure mode. You typoed this. Boom, pass rod equals. You run this thing without debugging, it's infuriating. It's terrible. It's going to drive you crazy. It can take you hours to realize you typoed this stupid word. It has, I've been there. It sucks. Hard to say how to avoid it. Debug definitely helps. You can at least say, what's the latest thing that my program sent me? And then you can kind of see, okay, cross-correlate this to your script. What is your script doing at the time? And realize what's going on. Do you know how I solve these issues? Printf debugging. Boom, I know after A, we're fucked. And so I can go over here and I know it's here. The other way you can do it, that's less insane. If you run this in IPython, it has a --pdb flag. That means when you hit Control-C, instead of killing the script, it drops you into a debugger. Now, this debugger is inside pwnlib. That's kind of annoying. You need to learn how to use the Python debugger, but it is eminently usable. You can walk back up the stack, or actually, if you just do backtrace, that's too nice. You can walk all the way up the stack to see where you are in your process, and you can see exactly what read until is hanging. Very, very useful. Alternatively, even without that, if you do this and you hit Control-C, here's the stack trace. Here is going all the way up here. Here's what's failing. It's not always so simple to see what's going on from there. For example, you might have, they're just complex scenarios where printf debugging is still something that you want to do. I do quite a lot of it. What time is it? We have 7 more minutes. So pwntools, this should be enough for you to use pwntools to interact with these things. But you don't have to use pwntools. Oh, wait, one more thing I want to do. If you do this in a row here, let's say we just keep going, and you don't carefully clean up, you can run into a situation where, let's remove that sleep from my proc. Oh, it doesn't exist. Oh yeah, this is hanging on purpose. You can easily run into a situation where you're creating too many processes and you're not waiting to clean up. It can be a disaster. There are 2 ways to avoid this. You can wait on your process, which waits for it to finish, so you're not spamming the system with processes. You can kill the process, which also kills it, or you can use Python's built-in with statement. This opens a resource, lets you interact with it, and when you leave this block, it'll close the resource cleanly. pwntools supports that functionality as well. All right. That's probably all you need for this module in pwntools. You don't need to use pwntools in this module. I'd recommend it because it is good for the rest of the course. but you can use a different Python. pwntools is a hacker library. It's all very hip and awesome, but like it is specifically mostly used in cybersecurity context. Subprocess is the built-in Python library for dealing with subprocesses. And the way that, and pwntools uses subprocess under the hood. The way that you launch a process with subprocess is using popen. You can launch your myproc, and I'll show you how this failed. And then, of course, I'll show you how this fails. It doesn't fail. Oh, I guess that, okay. Yeah, anyways, you launch your process, and then one thing that you might have noticed is the process started spewing output right into our terminal rather than into the Python script. So now you need to do complex stuff, well, not complex stuff. You need to explicitly redirect output. This is a special placeholder value that says create a new pipe for me to interact with. Pipe this into Python, basically, or into a file script that I can access from Python. It becomes std out, and you can read from it here. Okay, now what's going on? Why is read not returning? Because it is trying to read. This prints something, right? Well, this is why pwntools was created. It's annoying things like that. So let's limit our read to some amount of bytes. Yeah. So let's also, okay, let's say we read. So we got to read 12 bytes because it was trying to read until there's no more to read. That's like a read all. Of course, it was hanging because the process is waiting for input. So now we manually have to read out 12 bytes. And then we have to build a string, the password string, reading one character at a time until we have a new line. Okay. And now we can at least print the password out. What? Why didn't it like that? Oh, only concatenate string. Okay. These have to be bytes. Hit Python 3 with a string. Okay, so we can get the password. And now we can do p.stdin.write. So we write into the process standard in this password. And since we don't have a send line, we need to add a new line. Okay. Boom. None type. stdin is none. Why? Well, we didn't intentionally, explicitly say redirect stdin. So we also need to do that. So you can see this is getting annoying. Okay, now it doesn't automatically convert strings and bytes. So now we have to say, okay, this is bytes, this is bytes. Okay, boom, password. And then we std out.read the rest. Run this. p.std out, not the password, the process. All right, we're hung. Why the hell are we hung? No one knows. And there's no debuggability. So this gets very, very annoying, but you can use it. We're hung in this case because I sent, well, that shouldn't matter. One thing that I did, I sent the string pw instead of the variable pw. Are we still hung? We're still hung. I mean, let's read out some bytes instead. Ah. Okay, let's wait on this guy. What's going on here? It reads. Maybe we didn't flush. Is it possible that we didn't flush? Yes, because we didn't flush. So you have to buffer the read. You have to flush the read. Otherwise, it sits in a buffer. It's just really annoying to use subprocess for this sort of one-off arbitrary interactions. I highly recommend using pwntools. Look at this comparison. Here is the pwntools version. Here's the subprocess version. They're not equivalent scripts, but as you saw, subprocess more complex. No debug. It's built for a different purpose. No debuggability, etc. All right. Any final questions? All right. Go forth, finish crypto and access control, and we'll see you next week for Computing 101. Goodbye.